Okay, here's our outline for today. I think we'll probably be able to dismiss a little early today. We're doing good on the schedule. Um, and when we finish talking about moment of inertia today, in terms of angular momentum and spin angular momentum, it'll be a good point to break instruction and then dismiss. So you'll have a big homework assignment, kind of a combo assignment on stuff that we talk about today, and then some review stuff to get ready for the exam. And in terms of the exam, normally I admonish you or I instruct you to go to SI, but there's a little bit of a change in the SI schedule today. There's no regular SI. However, they are going to have um, exam 2 review today at 2:30 to 4:30 in Trevor Colburn Hall 351. Is that a lecture hall or is it a? Oh, okay. So up on third floor of the controversial Trevor Colburn Hall. So that'll be 2 hours of good review, and hopefully that'll help you get some better grades. Any questions about anything like that? Yes. Onto Canvas. Oh, onto her onto the. Oh boy. So you can put them in discussions. I don't care. All right. No, put them in discuss. Yeah. So you can put whatever you want in discussions. Oh, all right. Okay. All right. Okay. I thought it was the review guide or something like that. All right. All right. Good. All right. So we're clear on that. Also, I think now we have our exam on Tuesday, so you have all weekend, tomorrow, Saturday, Sunday, and Monday to study. Um, and you have a big study assignment coming up. The exam itself will be very similar in format to the first exam. There may be some more matching items in terms of equations and stuff. We are going to have a lot of different, or I have a lot of different equations and calculations that I can ask you about. Stopping time, stopping distance, downward speed on the table of gravitational potential energies. All this angular momentum stuff that we're doing today, and that we've done Tuesday as well. So we may not hit all of them, but we're going to hit several of them. So just be ready to, and the review set will help you get through all that stuff. I have a special review bundle that is quite helpful. All right, so as always, bring your raspberry colored Scantron with the UCF Pegasus logo on it, and we'll be filling up most of the first side. Bring your eye clicker. We'll be doing some clicking in class. And pencil and eraser and so forth as usual. No cell phones. So bring you're going to need a calculator. So bring that. Because you're going to have to do some square roots. Square roots are kind of hard to do by hand. So, I mean, you can do them, but it's laborious. So make sure you bring a calculator of some kind, but not your cell phone calculator. Okay, questions about exam 2? Okay, let's keep going. I want to go through a few basic thing about angle measurements here, something that you may not be familiar with, specifically the radian measurement system. We'll just go through the basics of it today. Now, I think most everybody knows the degree system for measuring an angle. You know, like this is an angle up here with a little arrow, curved arrow there. So 360 degrees for one full circle, one full so if we're spinning or something, we would say a revolution instead of a circumference. But and revolutions, that means one full spin, okay, of the merry-go-round. Now the third system. Well, let me just mention this. The angular speed of something that's spinning can be expressed in degrees per second, which you had on homework. It can also be described in revolutions per second, or more commonly, revolutions per minute. So the tachometer on your car, if you have one, will read so many hundred RPMs for whatever the engine is doing. Okay, so RPMs, that's in number 2. Degrees per second you had for homework, that's in number 1. And I want to introduce radians to you because it's kind of handy for what we're about to do with angular momentum. Now, it's defined in the following way. It's either the circumference divided by the radius of whatever circle you're following, or if you're only going a little bit of the circle, the little arc length that you are going divided by the radius. Kelsey, question. Well, revolutions just means, the normal thing. One revolution means one full spin. One full lap around the track. One full orbit around the sun. It's, and that's because we use this idea of revolutions per minute frequently. But we're going to use arc length and radians today. So whatever the angle is, so for instance, this little black curvaceous arrow here is the arc length for the angle that's represented here. So this, get my cursor over here. This angle here, so this is the angle right here where my cursor is, right by the dot. This dot here is the center of the circle. And then here's the radius, and these other two are radii. And then this curved arrow here represents the arc length. And it's precise. I laid it out along the arc of the circle, right on top of it, and then I moved it a few pixels to the right so you could actually see it distinct from the red circle. All right. Now, you divide that by the radius, and in the radian system, whatever you come up with numerically, that's equal to your radian system measurement for the angle. So one full revolution is 2 pi radians, all right? And half a circle is going to be another multiple of pi radians, all right? So one full revolution is 2 pi. And let's do a clicker question, all right? Turn your clicker on, frequency DD, and here's your question number 1 for today. All right, one full revolution is 2 pi. How much is half a revolution? And there you've got some multiples of pi. Give me. All right, try it again. All right, there we go. We got your answers now. So how much is half a circle? In other words, 180 degrees of travel, half a trip around the circle. Pi over 2, 3 pi over 2, or pi over 3? Take a look at what you guys are voting for. 15 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, that's good. Yeah, the answer is pi, and that's how you would represent, or you could write down 3.14 if you wanted to do it numerically. A lot of times you'll see just the symbol pi. Sometimes you'll see, people write down, 3.14 or 157, blah, 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 if they want. Now, if you are wondering to yourself, Dr. B, how did you do that? Well, I'll take away that short arc, and here's a half circle. And again, I did this one precisely and budged it a little bit upward so you can see it distinct from the circle. But that blue arc represents half a circle. All right. And in radians, it's arc length divided by radius. All right. So the arc length is half a circle. We don't know what the radius is here. It could be 2 millimeters or 2 light years or whatever. But whatever it is, half of, a half circle right here, half a revolution is pi r. A full revolution would be 2 pi r. So half one is just pi r, 1 pi r. Okay? And then you divide that by r, and you're left with pi. Okay? So jot that down if you got this one wrong, and jot it down if you want to make sure you know how to do this at any time. Now I have another method we're going to try out with clickers as well in just a second, but let me pause for questions here because it's a little bit tricky until you get the hang of it. Yes. The arc length is this full, we're talking about a half circle, okay? So it's this blue arc, so however many centimeters, meters, kilometers. Yeah, so we're talking about a half, yeah, so how much would a half circle be or a half revolution? Okay, so that's what, so that's what that is. So if I tell you what R is, you could figure out, how many feet, meters, inches, centimeters, nanometers, kilometers, light years, or whatever it happens to be. Okay. But whatever it is, it goes into this quotient here. And the cool thing is that in the radian system, the radius drops out. You can see it here in this third part of the equation block, Deanna. This R here in the numerator and the R in the denominator from the definition, they totally cancel. So you're just left with pi. Another question. No. In fact, this definition here, angle in radians equals arc length of radius, probably will be on the cover page. So, yeah, because this is not a geometry class, so I'm going over it. I want to make sure I go nice and. Question. No, sometimes you only know the degrees in your, what if I say, okay, how big is this, angle? It's 33 degrees. It's not a half. So, I might not say, well, a half circle or a quarter circle or some convenient fraction of a circle. I might give you some number of degrees. In that case, you go with this formula. All right. Right here. So this is another one that you can use. And it's just proportionality. Okay. So if you know the angle in degrees, like the little slivery angle that I had before, that was 20 degrees. All right. And we're going to do that in a minute. So your master proportion is pi over 180 degrees. And so if you know the denominator on the right side here, like 20 degrees or 27.38 degrees or whatever it happens to be, you can figure out the numerator in radians. So does Does that appeal to you? It does, but it's the same radian based on arc length principle, but now it's even simpler. We're just going straight because it's a straight conversion. Pi radians in the numerator up here is the same as 180 degrees, and they're proportional. So like pi over 2, check this out. Pi over 2 would be 90 degrees because pi is 180, so half of that is 90 degrees. All right, question. Can I do what? By memorizing the unit circle? What is that? See, because you've had trig and calculus class, but not everybody in here has. Yeah, you could. I mean, if you know, this is based, the what is your first name again? Morgan. What Morgan is mentioning is something from trig class, which is the unit circle, a theoretical circle of radius equal to 1 unit. And so the circumference is therefore 2 pi times 1, or just 2 pi. And so the length of your arc on that circle is equal to your angle measurement that makes the arc on the circle. But we're not going to miss with the unit circle, although I'm very happy that you know about it. But this one, what if you have 37 degrees? I mean, that's not going to be on your unit circle. You got to do this. I mean, eventually. So here's your next question. Okay, in radians, so use the proportion now. 1 full 360 revolution is 2 pi. How much is this circle? And this one's 20 degrees. How much is this? Whoa, I better change that. Hold on a second. Don't attempt anything. I gotta change the. Okay, how many radians is this 20-degree angle? All right, go ahead and start. And maybe hit refresh if you're not getting your. There's still multiple choice. So use that proportion that we just had. Pi over 80 equals angle in radians divided by 20 degrees. And you're just going to solve it. Which there's a couple ways to do it, but it involves a little cross multiplication, as proportions frequently do. Or you could do it mentally, mental arithmetic, if you're. But see now, Morgan, this one's not going to be on the standard unit circle in your trig book. So. And but I'll give you some stuff so you don't have to flail with radians and stuff. And the thing is, figuring out the angle is not the important thing here. We're doing this to set up a formula, an equation that'll make sense. Okay, 1 minute. No, 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 no. Na, 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 na. La, 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 la. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Let's stop it. me see what you guys voted for. Yeah, pretty good. You did good. The answer is pi over 9 or 0. Hey, who put down 0.349? Anybody actually calculate it out? Yeah, okay, good. Yeah, that's kosher. That's good. You can do that. And here's how it works out. Okay, so here's your proportion. And we have 20 degrees down in the denominator on the right side. Now that's given to you. I designed this graphic over here, this circle, so that this other radius here was 20 degrees tilted from horizontal. Okay, so I did that. All right, so down here in the proportion, you know that this is 20. All right, and you want to figure out angle theta, in other words, your unknown angle. Okay, in rate, I mean, it's not really unknown, you're just kind of converting it. All right, so that means that you cross multiply, 20 over to the left, and you get 20 degrees times pi divided by 180. All right, so go ahead and jot that down if you got tripped up on this question. Although a good fraction of you did, 77% did get this right. All right, so that's good. All right, now, so that's cross multiplying at this stage. Now, the last step, I mean, right here, you can go 20 times the pi button divided by 180, and you'll get 0.349 approximately. Or you could just reduce the fraction and get pi over 9. All right, so let me ask you, here's a mental IQ test. Raise your hand if you want to venture an answer. Okay, 180 degrees is pi, 360 degrees is 2 pi, and I already mentioned that 90 degrees is pi over 2. What's 45 degrees? What would 45 degrees be? Somebody that's not in engineering. Okay. Who wants to venture a guess? Go ahead. Yeah, pi over 4. Okay. Now, pi over 3. Okay, back to the back row. How much? Yeah, 60. And pi over 3 is the same as 180 over 3, 60 degrees. So that's good. All right, now, 1 RPM in radians per second, so if your angular speed omega is 1 RPM, then that's like having 2 pi radians divided by 60 seconds. So that'd be like about, that'd be about 0.05. Can somebody calculate that? 2 times pi divided by 60 should come out pretty close to 0.05. Am I right? Did I overestimate? 2 times the pi button divided by 60. What do you come up with? Who's got it? 2 times the pi button divided by 60. What do you got? 0.104? What? Oh yeah, that's right, because it's 2 pi. Okay, I was thinking pi over 60. Okay, so 2 pi. So 2 pi is 6.28 divided. Okay, so it's going to be closer to 0.1. Okay, good. All right, so it's going to be some number per second. Angular velocity is always rated in per second. Kelsey. The W, that's not a W, it's an omega. It's a curvaceous W, lowercase Greek letter omega. Right now, in general, so 1 RPM, that means 1 RPM, that means you make 1 full circle for every minute, every 60 seconds. In general, omega is 2 pi, full trip around, divided by how much time it takes, so capital T. And just make a side note to yourself, omega, the angular velocity is always going to be in per seconds, or seconds to the -1, if you will. The fancy scientific name for per second, or seconds to the -1, is Hertz. Hz is the symbol, and it's named after a German scientist named Hertz, Hertz, not the car rental firm. He's the guy that discovered or first observed electromagnetic waves. So here's your narration here. So up here, for 1 RPM, you have 1 revolution and in 1 minute. So that's your angular speed, the rate at which your angle changes. So if you're looking at something that's going 1 RPM, it's actually that's like looking at the second hand on your watch, right? Now, in general, you have the same thing over here for some other, maybe faster or slower than 1 RPM. But whatever it is, you put the capital T is down here in the denominator. All right. So that allows us to make use of these two versions of that last formula. Omega equals 2 pi over period, capital T. Or just as good, capital T is equal to 2 pi over omega. So either one of those is kosher. All right. And I may put this on your matching. All right. I might put it on the cover page, or I might put it on the matching. Now, the reason that I'm trotting you through this stuff is not because we're in a geometry class, but we need some extra geometric tools to understand angular velocity and moment of inertia. So let's turn to that. Okay, let's look at this yellow pixel up here, this little chunk of this bicycle wheel. Okay, all right, so I sectioned it off and I colored it yellow. And let's say that this thing is going clockwise. Okay, the velocity of that pixel, the linear velocity, is tangential to the circular path. Okay, so it's going off in that, I don't know, it's about 2 o'clock maybe for direction for the velocity vector. And it's going to have a certain, it might have 5 RPMs or some other angular speed. Question? Tangential means it's along a tangent line, and the tangent line only touches at one precise point. It touches at the pixel. So right where the tail of that arrow is the point on a circle, that's, I didn't draw in the circle, but, you could, I could draw it in a yellow. And vector V is going to be tangential to the circle at that point. All right. So take the circle, take the point on the circle, mentally draw on a tangent line through that point, and then the velocity is either going to be going, it's either going to be going that way at about 2 o'clock, or it's going to be going this way but that's if it's going counterclockwise. Okay, so it could be going 2 o'clock or 8 o'clock on the dial, but we're choosing clockwise just for just for something specific. Now, angular speed and angular velocity are related. Angular velocity is a vector, but it's a special kind of a vector, and the direction of it, it's not going to be parallel to the velocity at any point. It's actually going to be oriented to the spin axis, or the axis under consideration, right? And you use something called the right-hand rule for the angular velocity vector, omega, right? So here's the right-hand rule. You take your right-hand rule, you take your right hand, and you curve your fingers in the sense that the bicycle wheel, or whatever it is turning. So if it's turning counterclockwise like this, then the vector is out of the screen or toward you in the direction of your right thumb. So your fingers follow the path, and your thumb of your right hand gives you the direction, And we symbolize that. If it was going counterclockwise, it would be symbolized by a circle with a dot. Now this one's going clockwise. All right, so what I do with this, again, I put my fingers in the sense of rotation. So the fingers of my right hand, okay, so like this, okay, it's rotating like this. And the thumb of my right hand now is going into the display screen or away from you guys. All right. And that is symbolized with um, a circle with an X in it. All right. So now the circle with the dot and the circle with the X are meant to represent an arrow. Now an arrow has a point at the front, because it's an arrow. You're hunting bison out on the Great Plains. You got to get it with a good arrowhead. So you got a dot at the center. But at the back end of the arrow are some feathers, for fledging, okay, to make it go straight. All right. And that's what the X represents. So if something like this, if the arrow is going away from you, you see you see the feathers. And that's what the X stands for, the four feathers of your arrow. But if it's coming straight at you, counterclockwise, you're seeing the arrowhead. So you're seeing the tip of the arrowhead. That's the dot in the center of the circle. Question. CCW means counterclockwise. And CW means clockwise. Sorry. Yeah, it's good. Yeah, clockwise and counterclockwise. All right. Now, this brings me to, and you know what? I'm going to ask you maybe one or two basic questions on the right-hand rule on the test. And I'm going to be watching you like a hawk because because of something that happened to me in grad school. I was studying for this big written exam that they give you the first year of grad school. And, I had this study outline, like a Shams outline and, like the different, like if you're studying for SAT, you have a study guide for that. And, you work on problems and stuff. So I was working on all these physics problems and I was doing, I don't know, some angular momentum or something. And I'm there writing at my desk and, working my calculator, trying to calculate everything. And I kept coming up with the wrong answer. And I said, and I did another problem. And I looked up the answer, because these study guides, they have the answer in the back. So you do the problem, you look it up in the back. And if you don't get it right, then you ask your grad student, your fellow grad student, across the aisle, what am I doing wrong here? And so what happened was I was writing with my right hand and I was doing my right hand rule thing, figuring out my right hand rule with my left hand. So I was always wrong, exactly wrong. If it was supposed to be an X, I was getting a dot. If it was supposed to be a dot, I was getting an X. So that being the case, if I see anybody on Tuesday going like this with their left hand, I will actually help you on the test. And I will say, no, use the right hand. Okay? The only time I ever help students on tests. Otherwise, you got to know it all yourself. Right? So remember to use right hand. This right hand. Your regular right hand, not the other right hand. So use this one. All right? And I'll give you some homework tonight, to try to. I'm humble about it because I was humbled in grad school that one time. It's embarrassing. Yeah, 'cause my office mate said, "Yeah, knucklehead, you're doing the right hand rule by using your left hand. How about trying the?" So I got blazed for that question. What? Yeah, so if you go counterclockwise, your thumb is sticking out. My thumb, anyways, is sticking out from the computer screen towards you. But now, if it were going clockwise like this, it'd be, yeah. So don't dislocate your shoulder while you're doing it, or don't try not to get, an early onset of carpal tunnel. Yeah, the right fingers, you're right. your fingers can only curl one way. And so your right hand, you know, so you can't take your fingers and curl them the other way. I mean, well, a little bit, but, this is the normal way of curling your right fingers. If the thumb's pointing towards you, it's the dot. And if you have to do this, it's pointing away from you, then it's the, no. If the, Morgan! All right. If the, Now, if I'm looking at this screen up here, which is the other direction, then yes, I get the dot when it's pointing towards me. And I get the dot when it's pointing, towards you, when you do it like this. Okay. Now this one, the sense is on this computer screen, like that, so that you get the X. It's going away from you. Yeah, so the arrow's going away from you, so you see the feathers on the arrow. That's the X. Yeah, it's just what we just did. You'll see on the homework. You'll see on the homework. It's just, yeah. I won't make it tricky. I probably won't make it in perspective or anything like that. So it'll be about as clear as this. Now let's keep going. Okay, so what you would do is you would just write down an X somewhere, or you would, actually trace it in your diagram here, so this one's an X. All right. Now, the rotational period, if we know the RPMs, the angular speed, we can go 2 pi over the angular speed. And that'll be the amount of time it takes to make one full lap. All right. All right. Now that's important for us because now we want to talk about the regular velocity or the linear velocity. Okay, that's the red arrow V up there. Okay. And that is basically, that uniform circular motion, let's just say it's going at a constant RPM, constant angular rate. Okay, so whatever the circumference is, it's it's 2 pi times the radius, and then the amount of time it takes is capital T, for one revolution. All right, now we're going to use that formula that we just developed. Instead of that T in the denominator, we're going to put in 2 pi over omega down there in the denominator. Nice. Now, I want you to look at that carefully. That third part of the equation block. Is there anything in there that strikes you as particularly handy? What do you see? Yep. Let's burn them on out of there. Okay, so cancel your 2 pi's. And hey, that omega is in the denominator of the denominator, so that means it flips into the numerator. So you have R already in the numerator, numerator, and then omega goes into the numerator. And so this is a really important formula, V equals omega R. It relates the linear velocity to the angular velocity, at least magnitude-wise, all right? And so the linear speed and the angular speed, V and omega R. Now, because that is true, go ahead and put a big star next to that formula. That's going to really help us. And remember, the spin angular momentum is really just the sum of all the little orbital angular momentums of each pixel. So pixel by pixel, you have L equals mvr. Okay? I mean, that's the, for something that's going on a circular path like the bicycle wheel, mvr is perfect for orbital angular momentum. We talked about that on Tuesday. All right. And you got a zillion pixels. However you want to divide up the tire, into pixel gram by gram or 10 grams by 10 grams or any other division, you're going to have a bunch of these MVRs. And the total angular momentum of the bicycle wheel is just going to be the sum of all these MVRs. But now look at this. V is the same as omega R. That's the formula. And now we can turn an angular momentum, an orbital angular momentum, into a spin angular momentum, something that's oriented not to the orbital speed, but to the spin rate, to the angular speed and the angular velocity. And why is that? Because V is equal to omega R. So look at what we've got. We've got M, omega R, and then another factor. So we have, in terms of our geometric structure, we've got mass of the pixel times the square of the radius from the center to the pixel, whatever that happens to be, 20 inches or 20 light years, all right? And that quantity, mr squared, at least for a rigid object, is a constant, pixel by pixel. So every pixel, if it's a rigid object, is going to have an mr squared. So it might be 1 gram times 20 centimeters quantity squared. And then, further along the tire, you've got another 20 grams, or 1 gram times 20 centimeters quantity squared, and then all the way around. And you add all those up, and you're going to have a pile of mr squareds. And collectively, those are known as the, so the sum of all the mr squareds is equal to something called the moment of inertia, all right? And the angular momentum is equal to that quantity, moment of inertia, capital I, times the spin rate, the angular velocity. The angular momentum, my wonderful students, I don't have it here on the diagram, but the angular momentum is in the same direction as the angular velocity. So for that bicycle wheel that we were working with, it was going clockwise, so the angular momentum would be into the board as well, into the screen, right? But it just depends on what you're doing. Now, if you look at these two barbells, you can see that they're going to be different. One of them is going to be easier to spin than the other. One of them is going to be easier to slow down than the other. If you spin, so if you hang them from a little wire represented by the dotted line and spin. Now, Kelsey, on this one, they're spinning around that axis, the dotted line axis. And this is a little trickier because it's perspective. But this one is meant to be this sense. Okay, so the angular velocity is up in both of these pictures. Okay. All right. Now, which one is easier to spin up and which one is easier to, or harder to spin up or to slow down? The one that's easier is 45 centimeters, the one on the left. Because the r squared, most of the r squared is 45 centimeters away. But for the other one, or I should say 22.5 centimeters away. But for the other one, most of the, out there where the weight is, the two weights on left and right, they're out there 30 centimeters away. So R is 30 centimeters for the one on the right, and it's 22.5. So 30 squared and 22.5 squared, 30 squared is bigger. So it has a bigger moment of inertia. And my wonderful students, if your moment of inertia is bigger, it's harder to get it going. It's harder to spin it up. If it's smaller, it's a little bit easier to spin it up or to slow it down, to change its angular momentum state. All right, now let's calculate a simple moment of inertia here. Hold on, question. What's that big what? Oh, this? That's a Greek letter sigma. Yeah, that means, I'm sorry, thank you for pointing that out. That Greek letter sigma stands for S, which stands for sum, S-U-M. So it's the sum of all the, so you calculate MR squared, Kelsey, for each pixel, and then you add them all up. All right, that's kind of what I've been talking about. And sorry, yeah, I forgot to mention, this symbol means sum over all the pixels. So if you've divided your, your bicycle wheel into 100 pixels, or like 360, 1 degree per pixel, then you have to add 300, you have to do 360 MR squareds and then add them up. And then that's your total moment of inertia. Question? Yes, but not in the way that you're thinking. The question is MR squared related to 1/2 mv squared? And the answer is yes. We're calculating here angular momentum, okay? If we did a similar calculation for kinetic energy of something that's spinning, here's what you get. Kinetic energy is 1/2 times I, moment of inertia, times omega squared. Exact analog. All right, so go ahead and write that down. Kinetic energy, 1/2 I omega squared. I might give you a little homework problem about that. I don't usually emphasize that part, but since Matt, it's Matt, right? No, Kelly, Brian Kelly. Yeah, Brian, Brian Ryan. What? Ryan Kelly? Your first name is Ryan? Okay, I thought it was something like that. Ryan Collins. Man, I was flailing there. Okay, so Ryan Collins asked about kinetic energy, and it's similar. All right. Question in the back, just a second. Yeah, kinetic energy of something spinning, 1/2 times the moment of inertia I times omega squared. 1/2 I omega squared. The angular momentum, I mean, this is, see here, regular momentum is mv, right? So this is the rotational analog of regular momentum. So I is like the rotational analog of the mass. But it's not just the mass, it's kilograms times the square of the distance from your spin axis. So here's something that I want you to remember. The mass and the arrangement thereof, all the R squareds, affects your angular momentum, your angular kinetic energy, et cetera, et cetera. All right. So in Newton's laws, F equals ma, all you care about is the mass. It's a rigid object, point particle, blah, blah, blah. But when something's spinning, you not only have the mass of each pixel, you have how far it is, and you're actually squaring it and then adding them all up to get the moment of inertia. So it's kinetic energy 1/2 I omega squared. Now let's calculate a moment of inertia. Oh, wait a minute. There's a question up here. Okay. Let's calculate a simple moment of inertia. Okay, let's take, this is called a rigid rotator. And actually, we use this model to study the dynamics of simple molecules, like carbon monoxide, water, even water. And let's say that center to center, it's 4.20 meters. So we have two 7-kilogram blocks. And let's ignore the mass of the rod, right? We'll just say that it's really light. So much, much less than, so it's made of titanium. So it's nice and rigid, but really light, much, much less than 7 kilograms, okay? So let's calculate, let's put in my spin axis. I could put the spin axis anywhere I want, but this is always a good one, the one that goes through the center of symmetry, all right? And so R, we're going to do MR squared we're going to do 2 MR squareds. and they're going to be the same size. But let's get it scoped out here. So R is 2.10 for the mass on the left, is 2.10 for the mass on the right. All right. So now what we got to do is square, do MR squared for each of them. So here's what that looks like. All right, I'll park that over to the right a little bit. Okay, so the moment of inertia, I, is the sum, sigma, capital Greek letter sigma, over two masses of mr squared. So we're just doing two calculations and then adding them up, mr squared. So it's mr squared is 7 kilograms times 2.10 meters, quantity squared, for the one on the left, and then the same for the one on the right. Now, if you have different masses, you'll come up with something different. But we got something that's, symmetric, for mass, symmetric for distances and stuff. Just for something fairly simple to calculate. But actually, this is a good model. We actually use it in quantum mechanics. So, not this big, but, they're much smaller. So, 2.10, can you verify that? 2.1 times 2.1 is 4.41. Anybody verify me on that? Raise your hand if you verify me on that. Okay, you got it. Anybody else? 2.1. Okay, good. Right, now multiply that by 7. So it's going to be a little bit bigger than 28. It works out to 30.87. And then you got another one the same size for the one on the right. So your moment of inertia is 61.74 kilogram meters squared. There's no unit for moment of inertia. Okay, there's a unit for, force, the Newton. There's a unit name for energy, the joule, but not for moment of inertia. That's just kilogram meters squared. All right, now multiply that by omega, and you'll have the angular momentum, the spin angular momentum if this thing is spinning. Multiply it by 1/2 and then omega squared, and you'll have the kinetic energy of spinning. So I might make some homework. I'll try to write a couple cinchy multiple choice questions about the kinetic energy of this system. I think that'll be good. And then you'll be able to see, how that momentum of how the kinetic energy works and stuff. It's kind of cool, actually. There's all kinds of interesting things about linear momentum and angular momentum and the rotational analogs. And, most people don't talk about it, but it's really related to the structure of space-time, the symmetries of space-time in 4 dimensions. And then, of course, there's one more symmetry in space-time, but you'd have to take relativity class for that. You'd have to work in 4 dimensions and stuff. So, in other words, trig out Morgan, you'd have to take 4-dimensional trig class. So, yeah, but if you did, if you had it with me, it'd be pretty interesting. I always love teaching that stuff. All right, so anyway, so this is where I want to finish. But let me ask for questions about this calculation. Go ahead. Yeah, you just have different numbers here and here. All right? All right, now, let me just give you one more instruction for the exam on Tuesday. Make sure to study diligently and well. There'll be a big combo homework this weekend, number 10. And try to hit discussions. I think there's going to be some new stuff coming out in discussions to help you with formulas and stuff. So pay very careful attention and participate if you can. All right, you're dismissed a little bit early today. Good. I'll see you next week.